Oh,
not moles.
why did you get it to grams?
Well, I got it to grams.
Okay.
So I could do the.
So there seems to be some questions about
Oh.
question 4 on page 4, right? So
Some discussion.
this is related back to experiment number 1. So you had
Also, can I have this data, please?
syringe,
I was under the impression you had that already.
and you initially had a volume of 5 cubic centimeters, right? Okay? And you're gonna try and figure out the mass and the number of moles in here. So obviously that's gonna be a really, really small number, okay? Because you only have like basically 5 pinkies worth of gas inside of here. So you've got this conversion that 1 cubic meter is equal to 1.00 times 10 to the 6th cubic centimeters. And that works because 1 meter by 1 meter by 1 meter is 100 centimeters by 100 centimeters by 100 centimeters. So if you cube 100 centimeters, you get this. So obviously if you have 1 cubic meter, you're going to have a whole bunch of tiny little cubic centimeters within that. So you need to convert the cubic centimeters into meters. You've got to know that the number of cubic centimeters, the number of cubic meters is going to be really, 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 really small number. Okay? So then you've got the density. Today is going to spend a lot of time talking about density today. So density in physics we usually use rho is mass over volume. So you know the volume, you know the density, then you can find the mass of the gas inside the syringe. Once you get that, then you can go, okay, well 22% of that is oxygen, 78% of that is nitrogen. Now, is it diatomic, Cohen?
Yes.
Yes, okay, but that's taken into account when I tell you that the molar mass of oxygen
that makes sense.
is 32.0 grams per mole.
Oh yeah, because O is just 16.
Yeah, O is
I know.
16.
I knew that. My brain was just not braining.
And that's why nitrogen is, wait for it, 28, because nitrogen is 14.
Yeah.
Awesome.
So that's what that's taken into account.
Okay.
Okay? Cool with that?
Yes.
Okay. So then when you get to number 5, because of the fact that this is an isothermal process, and if you look at pressure volume, this is going to be a curved line like this. So you're trying to find the area underneath there, and without doing all the calculus, you have this handy dandy little equation that says work equals nRT, natural log of VI over VF. And then it's just a matter of plugging numbers into that. Now, when you get to question number 6, okay, there's a couple of ways you can approach number 6. How the graph changed if the experiment had been run at a higher temperature. One option is that you just look at this and you go, oh, there's a bigger value of T. Mathematically, I'm going to get a bigger value of work. Okay, so from a pure mathematical standpoint, you just can say, oh, I'm multiplied by a bigger temperature. The other way that you can view that is more of a bigger picture and go, well, at a higher temperature, if you have the same volumes, if you have a higher temperature, what's going to happen to those pressures?
They'll also increase.
Yeah, so then what would happen is that you would shift this line up.
But the
Okay.
slope of that line would stay the same.
Huh?
But that rate of change would be the same.
Yes, but then you're going to have a bigger area underneath that line. So those are the two ways that you can handle that one. Anyway, so there's all of that. The rest of it should be fairly straightforward. Any questions on the lab? And like I said, with some of those graphs, it's handy, especially if you have that one that involves temperature. you can do those little squiggly line breaks to indicate that there's like a break, cause otherwise, cause what was your lowest temperature that you all did?
293?
Yeah, 293. Well, if you're lower, if you got to go 0 and then all the way up to like 10, 20, what, up to 200, you got a whole bunch of space with no numbers in it. So that's why I said you can just do that little deal and say, okay, that maybe you started at 200, and then because then you started at 200. What was the next what was the range of your temperatures?
293 to like 342 is that max?
Yeah. So then within that, then that allows you to spread those temperatures out over a larger area because you don't have to take up all of that space with the with a whole bunch of areas where you're not going to have any numbers. Okay? We're good. Staple the graphs to the back. Make sure that you tell me which graph is which, like experiment 1, experiment 2, experiment 3. Okay? So make sure that you indicate that on the graph. Okay, so stop you on the camera, and that'll give us a break.